For our last topic related to strings, we are going to talk about some basic string data structures that make certain operations on strings much easier. And in particular, we're going to talk about a data structure called the try, another one that is the suffix tree, which is sort of an extension of a suffix try. And then we will talk about the suffix array. And each of these allows you to do certain operations related to strings a little bit more efficiently or more usefully so that you can perform additional computations after you have that structure on them. Sometimes they're not the most efficient structure just all on their own if you just want to do one thing, but they allow you to do a lot of other things as a result. So let's talk about each of them. So the first idea is the one called a try. And I think that's the right pronunciation, at least that's the way I learned it. But I'm not actually sure that it's try. Yeah, anyway, a try. And what a try is it's basically a rooted tree where each node has 26 possible children. And that is one for each letter. Now, if you remember, when we talked about strings earlier, we said a lot of string algorithms apply to other types of data as well, because a string is just a list of characters in a row. Well, this is where we start getting into cases where it really does matter that we've only got a limited number of characters to choose from. So, for instance, if we're doing words in the English language, we only have 26 letters. And so we have a limit on at most 26 children per node. So the try, it's a rooted tree. Each tree can have 26 possible children, and those are one for each letter. So the first one will be A, the second one will be B, the third one will be C, and so on. And what we have is the root is, well, instead of saying it is, it corresponds to an empty string. And then basically you form a string, by following a path from the root to a descendant. Okay, so this is a rooted tree. It's one where we have a root at the beginning and we can follow the path down. And basically we will form a string out of this because each link that we follow, each child corresponds to one letter. So this might be the word A, or the letter A, and then maybe it's P, P, L, E, S. And so that would be the string apples, okay, as a possible example. Each node can be marked as either in or not. Okay, so if it's in, it means that node, and an in node means that node terminates a string. Now, as we'll see in just a second, that does not mean that is the only, that it can't have children and we stop descent and we can't descend any farther than that. But it indicates that a string that ends at that node is a valid string. And so you can think of a try as a way of forming a dictionary or something like that. So let's do a very quick example. I'll pick a few different words and we can see what they are. So let's say we have the words car and cat, and we have ape and apple, and the word apex Okay, so there's just 5 words. I think 5 would be enough to illustrate this. So we will have our root node that corresponds to the empty string. We'll have children. In this case, there's only going to be 2 children that we worry about at the first level. But just so that we can see them, we will have the A child, and we're going to have the C child. And then notice that, for instance, at this node right here, that node corresponds to the string that is just the letter A. And this node over here corresponds to the string that's just the letter C. But neither of those is an actual word, so neither one would be marked as in. But our word car, you can imagine that C has a child A. So now this is the string CA. And then we will actually have 2 different children. We'll have an R and a T. Okay, and both of these we will mark as valid nodes. So we mark them as in. And so what that means is if we trace a path from the root down and we get CAR or we get CAT, either of those is going to be a valid string in our dictionary. And so you can imagine how this might be extended over here. So we had the word A, and then P, and then we had an E. This was the word ape. We could also have the word APP, and then LE. It's a little hard to see it at this point. I'll make that a little bit bigger. APPLE. And that will be the valid word apple. And then the word apex will be APEX. So that's also a valid word. Okay, so notice that we have 5 valid words. Notice there that this last case where we had an interior node, E, that still has children. The interior node is a valid word, ape, and so is a word that extends it, like apex. Okay, so that's the idea of a try. And a try is a nice data structure because you can do a lot of things with it as far as checking to see whether a word exists. So if you want to see, does a word exist in the dictionary, you can follow the try down. If you want to find whether there is a particular say beginning part of a word, you can start following the tree. And for instance, you might be able to get a list of what the most common words that are descendants of any one node are. And if you keep track of like what are the 5 most common words that are the descendants of any one node, and 1, 2, 3, 4, 5, and you update those as you add new words in about which ones are more or less common, well, then as you are typing, if someone types a C, you have 5 suggestions for possible words that they might want next out of that. And so if you can maintain a try structure, you can do things like suggest an autocomplete. Like, oh, maybe this is the word you're looking for because those are the words that tend to be typed in this way. So that's an example of how you can use it. You can store other data here. For instance, if I store the number at any one point and sort of add it up as I enter stuff, that will help me know how many descendants I might have. There's a variety of other things that you can do. Now, if the only thing that you're wanting to do with the try is determine is a word in the dictionary or not, notice that it can take that if you have a string of length m, you're going to have to follow m levels. It's going to take time m just to see if that's in the try or not. And you can generally do the same thing by computing a hash of m and using a hash table, and it's about the same length of time. So a lot of people say, why would I use a try when I could use a hash table and get sort of the same results? And sometimes that's true. So there are cases where storing your words, instead of storing them in a data structure like a try, instead storing them in a hash table might be more efficient. However, there's things you can do with a try that you can't do with a hash table. Okay, so some of those autocomplete things that I mentioned there, those are trickier. You can store them, but you have to store all of the interior nodes, and it doesn't help you a lot. But that autocomplete, the try is the natural way of doing it. And Actually, in the worst case, a try is more efficient than a hash table. If the hash table has a ton of collisions, just one collision after the other, the process of resolving those collisions in the hash table actually takes more time, whereas try, you're guaranteed that any valid word is exactly the depth equal to the number of letters in the word. Okay, so there are good reasons for using a try. It's a pretty simple thing that you can implement. I'm actually going to do an example implementing this in class so that you can see how you might implement one yourself. And so you can watch that video separately where I code that up. Now, one interesting thing that you can do is you can form what's called a suffix try. You might be wondering, why would we want this thing? Well, first of all, you're probably wondering, what is this thing? Okay, and the idea of a suffix try is that we take some word and we're going to put that into a try, but we're going to put in every suffix, every possible suffix of that word also into the try. So let's give an example. Let's just take a string, and this is usually done for strings, not words, but I'll pick a word here. And let's say that we have a word like iterate. Okay, so iterate is our word. And then what are the suffixes of iterate? Well, it's T-E-R-A-T-E and E-R-A-T-E and R-A-T-E and A-T-E and T-E and E. Okay, so those in fact are those are them. Okay, so I'll form all of the possible suffixes of this suffix. And then if I wanted to, I could create a try that I insert all of the suffixes into the try. Okay. So let's see what we would get there. So we have one example over here where we had A, and then it looks like it was T, E. There's and that will be a valid word there. There's the single letter E. Oh, sorry. There is the single letter E, and that's a valid word, or that's a valid suffix. There is also E, R, A, T, E. So that is also a valid word. There is, let's see, what's another one? There's actually iterate. Okay, so there's the word iterate. There is the, let's see, what are some of the other ones? There's rate. Okay, and then there is TE, which is a word, as is TERATE. Okay, so that would be our suffix try. So it's a try that we form by taking all of the suffixes of this word. And you might say, why would we ever want this? What's the purpose of having a suffix try? And the point is, once we have constructed the suffix try, there are things that we can do that are much more easily. And so in particular, imagine that you want to find a substring and see if a substring exists. So for instance, I want to know, does the word era appear inside iterate? Okay, and so what I can do is I can actually go through, starting here, and I can follow and see, is ERA actually in the suffix try? And it is. ER and A are all in the suffix try, and that means that ERA is a substring of iterate. And so that becomes a very fast check. I don't have to go through. Remember that the other option was if I had iterate, I would sort of go through and I would check, well, is that ERA? No. Is that ERA? No. Is that ERA? Well, yes, it is at that point. Okay, but that's a lot of work to go through just to see is a substring, does it exist inside of here or not? So once we have that suffix try, we can do things with it. Now, the thing that you probably, if you look at this, you say, well, that thing's kind of a mess. That's not a very nice tree. It's got lots of long strings, and in fact, it's always going to have sort of a particularly long one, the longest equal to the length of the string, and one less than that, one less than that, one less than that. This is not ideal. Okay, and so there's another option that we have, and that is we can use a suffix tree. And so a suffix tree is a way that's sort of a variation on a suffix try. And I will say the reality is there are times that it's useful to use a try that we described up here. A try can be a very useful data structure. The concept of a suffix try or a suffix tree is very useful. So the idea behind it. But in practical terms, it is easier to use the suffix array and much faster to use the suffix array that we'll get to in a minute. So it's very rare that you would really want to program a suffix try or a suffix tree. Instead, you would use the suffix array when you want to do that. So really the two, I'll say, practically useful data structures here are the try and the suffix array, but it's very difficult to understand how to build a suffix array, and a lot of things are much more intuitive if you kind of picture them here as a suffix try or suffix tree. Okay, so let's talk about a suffix tree then. If we have a try, like the one here, we can turn that into a suffix tree by basically collapsing sequences of nodes that are all connected before there's a branch or something. So in this case, I could combine A, T, and E. I could combine all of those into one thing. I can't really combine anything beyond E because there I get to an ending answer, but I can combine R, A, T, and E there into a single node that will be a child. This one, I can collapse this entire long chain right here into a single node that has the value of iterate. So let me show you what the suffix tree version of this would look like. Okay, so I'll put this underneath and I'll keep moving back and forth so that we can see it. So over here we have one node, which is ATE, is what that edge is. The next one here, we have both E, and then we have R-A-T-E. Okay, the next one we have iterate, and then we have rate. So we have one here that is iterate. We have one over here that is just the word rate. And then way over here, we have one that is TE, and then one that follows on to that. So we have TE and RATE from there. Okay, and so you'll notice that in this case, each of these actually becomes basically each of those nodes in this example is a valid word. Now, in general, we can have a suffix tree where there might be an interior node that doesn't get split up. So it is possible to have a suffix tree where perhaps you go down to the letter E, and maybe the substring EV and EVER are both part of that, but just the plain E might not be. Okay, like so perhaps the word was reverse. Well, you then have EVERSE and VERSE and ERSE. And in this case, actually, there is an E on the end. So you might have an interior node, but you would also have those. You don't necessarily have that interior node. You might just have pieces of this along the way. Okay, so I hope that made some sense. The point here is that you're not guaranteed that every node in the suffix tree is a valid node. Sometimes you will still have things that are not valid, but each of the edges along here is an entire string. It is not just a single character. And so as a result, a node can have multiple children, and to actually see what the child is, you have to look at the string. So you have to store for each edge, you have to actually store an entire string and not just assume that it's a single character. Well, once you have the suffix tree, so now that we have a suffix tree, there are some things we can do. So for one, we can do just like with the suffix try, we can see if a substring exists by just looking at the particular nodes. Now, these are still going to be ordered alphabetically. Okay, so we're still going to have, at most 26 children. It's just a collapsed version of what we had before. There's not going to be new children created. So there's still at most 26 children. And for each of them, we can still check and see if something is there. So if I wanted to see if ERA was there, I can still go to E, and then down here, I'd see RA, and I would know, yes, that substring was part of this. Okay, so substring is still possible. We can count the number of matching substrings. So if we keep track along the way of how many nodes are at that level or below, so for instance, here we have, this would have the value 2 right here because there's 2 nodes that have that. This one would also have the value 2. This one would have the value 1, as would basically everything else. All of these are going to be 1s. Okay, but if we keep track of that, then for any substring, we can count how many substrings are there below that level. And so if I wanted to know, well, how many times does the substring ERA appear? If I go down this path and I say, well, I have ERA, I know that this link that I'm here on right here, this only has weight 1. There's only one thing down that path, so there's at most one thing. If I wanted to say how many substrings have the or how many times does the substring TE appear? Well, I can go over on this one and I say TE, and notice this link had weight 2, and because I didn't have to go down to any children, I know the answer is 2. And if I wanted to say, well, how many times does the substring TES appear? Okay, and just to be clear, this is an E. How many times does TES appear? So I look at the purple and I try to go down here. Well, there's not an S. It's R is the only word, and so the answer would be 0. Okay. So that's the idea of a suffix tree. So we could count matching substrings. We can find if a substring is there. We can find the longest repeating substring. So if we wanted to see what's the longest substring that gets repeated more than once? Well, in this case, it's TE. Okay, but generally the longest repeated substring is the deepest internal node of the suffix tree. Okay, and now when you want to actually measure what deepest is, you have to know how deep it is. So for instance, this node right here is 2 deep. Okay, this node right here is 4 deep. This node right here is 1 deep. That one there is 3 deep because of how many, basically how large the string is along that edge. So you do need to know the depth. Now, in this particular example, we have exactly 2 internal nodes. We have this one and we have that one. Those are the only internal nodes. Everything else is the leaf node. The root doesn't count because the empty string is a substring all over the place is the way to think of it. But ignoring the root, those are the only internal nodes we have in this case, and we want to say which one is deeper. Well, this one over here has depth 2, and this one up here has depth 1. So the one that's at depth 2 is the value, and therefore the substring TE is the longest repeated substring in our initial string, iterate. Okay, so we can go back and look through all that. Okay, so if we know the longest repeated substring, we can also get the longest common substring between two strings. And now notice this is different from the LCS problem that we talked about before. It's not the longest common subsequence. It's the longest common substring. Okay, so a substring has to be a contiguous set of characters. So if I've got my string here, it has to be a whole bunch of characters all in one region. A subsequence can say, I'm taking that character, that one, this one, this one. Okay, so that would be a subsequence. You know, it's just a selected piece of them. A substring is a contiguous set of elements. Okay, so the longest common substring between two strings, we can basically form a common suffix tree. Okay, but each node is marked separately as in or not for both strings. Okay, and so then what we have is the deepest node marked with both strings is the longest common substring. Okay, because what that means is that is a string that appears in both words. Okay, in other words, there is a suffix that is of that length or that starts with that length. And if it's marked in both strings, then it's the longest common substring. So it's a substring of both of them. Now, when we say it's in both of them, what that means is if we've got an internal node, so you can have a node, and you might say, let's say that the two are red and blue. So we might say that this node is in red, but it's not in blue, but maybe its child is in blue. Well, this is still sort of on a blue path, so this one would still be for both red and blue. Okay, so that one would still be marked for both red and blue. It's just not marked as in because it has a blue child. So it's a little bit tricky maybe to implement this sometimes, but it's possible to do all of this. The point is, once we have the suffix tree, we can do a whole bunch of operations on it much more easily. Okay, so now I want to introduce the last data type, and I'm not going to go through all of the details of how to create it because, to be quite honest, it's a complicated algorithm and very difficult to understand how it works to create it, but I'll explain to you what the structure is. So the structure is the suffix array. And the idea is, even though we could create suffix trees, and in fact, there's a way to do it in order n time, it's really complicated to code, and it's sort of a pain to do. And what we really need out of this is usually just a sorted list of the suffixes. So this is going to create a sorted list of suffixes. Okay, so if our word, kind of like before, was iterate, well, then the suffixes are terate, rate, rate, te, and e. And now, if I were to sort these, if I was just to take these and produce a sorted order from them, I would get ate, I would get e, I would get erate, I-T-E-R-A-T-E, R-A-T-E, T-E, and T-E-R-A-T-E. Okay, so there is the sorted list of the suffixes. Now, once I have that sorted list, okay, so you can think, how would I do this? Well, sort of, you could, the kind of the worst way of doing it that you can think of would be you actually create all of these as separate strings and then you sort the strings. And that would just be horrible. I mean, that's creating way, way, way too much data. What you actually would want to do, I mean, and this is not even the most efficient way of doing it, is you would want to sort the string starting at a particular index. Okay, so for instance, this is the string that starts at 0. This is the one that starts at 1. This is the one that starts at 2. This is the one that starts at 3. This is the one that starts at 4, the one that starts at 5, the one that starts at 6. Okay, and so each of these is going to be associated with where it came from originally, and you can keep track of that information. In fact, some of the algorithms that you want to perform on the suffix array, it's helpful to have that original information available to you. Okay, and so you can do a sort just based on numbers. So where you're actually where the end result instead of these strings is just these numbers right here. Okay, so where this is the thing that's there. And you can do that by defining a new comparison function, where basically you can say, if you're going to compare a number I with the number j, this is basically going to be comparing the string starting, and I shouldn't say the string, the suffix starting at I with the one starting at j. Okay, so you could define a new comparison function, and then you're just sorting numbers. Okay, so you're not going to get that 0 is less than 1, and 1 is less than 2, and 2 is less than 3, and so on. Instead, you're going to get, for instance, that 4 is the smallest number because the suffix starting at 4 is smaller than all of the other suffixes. Okay, so that's how you would sort of, that's still the naive way of implementing a suffix array and doing the sort, but you can do that. And if your strings are only 1,000 or so in length, if they're not too long, it's reasonable to actually do that sorting. The problem is that this is, that this comparison over here actually can take some time, and so it's not as easy to do this as you might otherwise think. Okay, so there is an implementation. It's not one I'm going to go into, but there's a very efficient way of doing this sort that's not just doing this part up here, and it involves using a stable sort, and it's sort of it's sort of a counting based sort that is going to first sort by the first letter, and then by 1 and 2, and then by 1 through 4, and then by 1 through 8, and so on. And so it sort of keeps doubling the range over which it is sorting each time. And it can do this efficiently. And the reason you can do it efficiently is if you have this stable sort, you can do these comparisons from one part of the string to a later part of the string, and it will be there. And the overall process is you can get this to actually just be an n log n sort, whereas it's not n log n if you have to actually define this comparison function that's not actually n log n. Okay, so the point is you can create suffix array by an order n log n search. If you want the details of that, I would look it up online or in the book. The book has some very nice code for doing it. It's very efficient, but like I said, it's a little bit difficult to actually see why this process works. So I'm not going to go through all the details of it right here. Okay, but once we have our suffix array, once we have this thing over here, the question is, what can we do with it? And we can actually do a lot of the things that we were going to do with a suffix tree, we can do with the suffix array. So for instance, if we want to find whether a particular substring exists in our larger string, we can search. In fact, we can do a binary search on the suffix array. So the example we had earlier was we were looking for the word era, E-R-A, to see if that was in here. And so we can perform a binary search, and the binary search would find basically that this word right here is the next biggest word, bigger than than era. Okay, and so by checking, and you might have to check two things, but basically by doing a binary search and then checking that word, you will find, oh yes, that does exist. ERA does exist. Those letters are in fact a part of this. Okay, and notice that if our original text, the sort of original string is size n, and the thing that we want to compare to is size m, the process here is going to just be log n times m in this case. So it's not that hard to find that. So log n to do the binary search on the suffix array. Obviously, there are n items and it's binary search, so it's log of n. And then to actually compare and check to see if a particular substring is there, you might have to check all m characters just to verify that each one is in there. Okay, so that's one example, is we can find whether a substring exists. We could also check to see, you could also check to see how many times it exists, because if you do a search, if there's something that appears multiple times, so let's just say that we wanted to find the substring TE, we could find here, and we would find here, and we could count that, okay, there's two. The first one starts with TE, the last one goes past TE, and we can do that along the way. We can do that to calculate how many of these things there are. Okay, there are some other things we can do with the suffix array. We can compute the longest common prefix. And again, I am not going to go through the details of this here because it can get a little bit tricky. It's definitely understandable. You can understand this if you read through the book and the algorithm that they use, but I'm not going to go through it right here. The longest common prefix. Okay, between adjacent suffixes. And basically that's going to tell us what's the biggest prefix that you can get between a string or between one of these entries in the suffix array and its parent. So for instance, here is 2 would be the longest common prefix between suffixes. And if we have the longest common prefix, and this is computable in order and time. You can basically compute it for all of them with one pass, but the algorithm for doing it is tricky. Once you have that, you can do something like get the longest repeated substring. And you can get that by just finding the what the biggest longest common prefix is, because that means that there are going to be 2 adjacent elements, and you find the one that has the longest common prefix, and that means that somewhere in the word, so remember, or not the word, somewhere in the string. So if we've got a big long string, each entry in the suffix array is some suffix. So we might have the green one, and we might have the blue one, and we might have the red one here. Those are all possible suffixes of this original string. And so if it turns out that green and blue and red are all next to each other after you sort them in the suffix array, and then it turns out that the longest common prefix between some pair of them is 10, like in other words, 10 characters match, then that would tell us that there's at least a substring that matches with 10 characters. So say it's green and red, we would take the first 10 characters of the green, we would take the first 10 characters of the red, and those should exactly match up. And that would mean that they would be adjacent to each other here in the suffix array. Okay, so you can get the longest repeated substring if you want to say, what's been repeated over and over. And then you can also get the longest common substring. So the longest common substring between two different strings. And this one's kind of interesting because you can do this by kind of concatenating the two strings together with some separator between them. So if I have some word like cat, and then I stick something in the middle here, and then I have dog, or maybe I'll say dag, just to make it easier. And I have some, symbol that I'll put in between them. So maybe I'll put a pound sign. Okay, well then when I form my suffix array, for each one, I will be able to determine, is it something that came from the first half or is it something that came from the last half based on the value. So if the value is from the first word, it would appear, it would have a value that's of the length of the first word or less. If it's from the second word, it would have a greater value. And so what you want to do is then you want to just find what is the longest common or longest repeated substring where they're from two different words. Okay, so you only look for a repeated substring if they come from the two different words. Okay, so the point is, if we have the suffix array, we can do a lot of things. We can identify substrings, we can find common substrings, we can find repeated substrings, we can do all of this, and we can do it very, very efficiently compared to what we would have to do if we just process the string in a straightforward manner. So if you get one thing out of all of this, the point should be that having some of these data structures for manipulating strings and storing them gives you faster algorithms as a result. And if you just use the naive sort of built-in operations and brute force your way to check stuff in a string, that will often be too slow. So you might need to do something like generate a suffix array and check through it, and that will be much faster than actually going through the original string. Okay, so that's all. Again, if you want to see how some of these are implemented, the try is very straightforward. I'll post an example of that. The suffix array is quite a bit more complicated, and you'll want to look at the process for doing that is described in our textbook, for instance.